evening, everyone. In this lecture of the subject Electrical Machines 2, KEE 503, I am going to discuss some numericals based upon the alternator or the synchronous generator. The numericals covered here are the basic numericals based upon the EMF equation of the alternator. So, for example, starting with question number 1. The armature coils of a 3-phase, 4-pole, 24-slot alternator are short-pitched by 1 slot. Determine distribution factor and pitch factor. So, before solving this numerical, let us just recall the concepts of distribution factor and the pitch factor. In this particular question, we need to determine the distribution factor of the winding and the pitch factor of the coils used in the armature winding of the alternator. The armature coil of a 3-phase, 4-pole, 24-slot alternator. Details of this are given to us. We are having a 3-phase machine, 4 number of poles, and the total number of slots over the periphery of the armature are 24. So, before proceeding to solve the question, let us discuss what is the distribution factor and what is the pitch factor. You might be remembering the EMF equation of alternator, which is given as E equals to 4.44 phi F TPH and TPH K. This is K. Here, K is the winding factor. K being the winding factor. Right? The winding factor is given as multiplication of KD and KC. Here, KD is the distribution factor and KC is the pitch factor or the coil span factor. You also recall the EMF equation of a transformer. In case of a transformer, the EMF equation was 4.44 phi M F T PH. In this equation, phi M was the peak value of the flux, core flux, F frequency of supply, and TPH was the number of turns connected in series, right? Here, in this particular equation, besides phi, F and TPH, we have got a factor called K. K is denoted as the winding factor and is given as the multiplication of pitch factor and the distribution factor. The pitch factor comes into picture if the coils are short-pitched. Short-pitched coils are the coils which are not the full-pitch coils, and the full-pitch coils are the coils which are having an angle of 180 degree between two sides of the coil, 180 degree electrical, right? So, if the two sides of a single coil occupy identical place, identical location under two adjacent poles M and S, then the coil is said to be the full pitch coil. The full pitch coil, the angle, the coil pitch for a full pitch coil is 180 degree. If the coil pitch is kept less than 180 degree, then coil is said to be the short pitched coil. The short pitching is done for certain reason. There are certain advantages of short pitching the coil. We will discuss those advantages in some other theory class where we will discuss the pitch factor and the EMF equation, pitch factor, distribution factor and the EMF equation of the alternator. The second term is the distribution factor, KD. The distribution factor comes into picture if the winding is distributed in nature rather than being concentrated in nature, right? So, if the winding is distributed in nature, then distribution factor comes into picture. If winding is not the distributed one, but the concentrated one, then all the turns of a coil side would be in a single slot on one side, and likewise the other side turns of the coil would be occupying their place in the second slot. So, to accommodate one phase winding, we would be having only two slots. One to have one coil side and the second to have the other coil side of the same coil. If the concentrated winding is used, then the total induced EMF is the arithmetic sum of the induced EMF in all the coils. But if in AC machines, in case of transformer, the winding is the concentrated winding. In case of transformer, the coils are the full-pitched coils, right? So, in case of transformer EMF equation, the term winding factor was not there. But in case of AC machines, the coils are the short-pitched coils and the winding is the distributed winding. So, as I said, in case of in case of concentrated winding, the total induced EMF across a winding would be equal to the arithmetic sum of induced EMF in each coil, right? Likewise, in case of full pitch coil, the total induced EMF will be the arithmetic sum of induced EMF in two coil sides, right? Now let us talk about if the winding is distributed one and if the coils are short-pitched coils, then what happens to the total induced EMF? So, if the winding is distributed, in that case, the total induced EMF across the two terminals of the winding would be the phasor sum of induced EMF in all the coils of the winding, right? Likewise, in case of short-pitch coil, right, the induced EMF would be the phasor sum of induced EMFs in the two coil sides of the coil. So, as we know, the phasor sum is less than the arithmetic sum of the induced EMF in case of distribution of the winding as well as in case of short-pitched coils. In both the cases, we are going to have a reduction in the total EMF that is available across the terminal of the winding or across the terminal of the coil, right? That reduction in the EMF is taken into account by two factors. The distribution factor takes into account the reduction of available EMF due to the distribution of the coils throughout the periphery of the machine. Likewise, the pitch factor takes into account the reduction of EMF due to short pitching of the coil, right? So, as we see the question, the number of phases given to us are 3, the number of poles are 4, the number of slots over the armature periphery are given as 24. So, number of slots per pole would be equal to 24 by 4. Now, short pitch, the angle alpha is the slot angle and the slot angle is given as 180 degree divided by number of slots per pole. 180 degree electrical divided by number of slots per pole. So, the slot angle comes out to be 30 degree electrical here. Now, pay attention in the language of the question. The coils are short pitched by one slot. So, the angle of short pitching of the coil is equal to 1 slot angle, right? So, angle of short pitching of coil is also equal to 30 degree. Otherwise, alpha is actually the slot angle, right? The angle, the electrical angle between two slots. Now, the number of slots per pole per phase. Number of slots per pole per phase. That is 24 divided by 4 into 3 comes out to be equal to 2. Now, let us concentrate upon the equation of distribution factor. The distribution factor is given as sin m alpha by 2 upon m sin alpha by 2. We have already defined m, we have already defined alpha. Alpha is the slot angle. Alpha is the slot angle. So sine m alpha by 2, m came out to be equal to 2. So 2 multiplied by 30 divided by 2. And in denominator, it's m sine alpha by 2. So 2 sine 30 degree by 2. Solving this, you will find that the value of distribution factor comes out to be 0.9659 approximately. Now let us pay attention over the equation of the pitch factor or the coil span factor. The angle by which the coil is short pitched is beta. So if beta is the angle of short pitching, then the pitch factor or coil span factor is given as cos beta by 2, right? In this particular question, it is given that coils are short pitched by one slot angle. The one slot angle was 30 degree. So in this particular case only, beta is equal to alpha, which is equal to 30 degree. Substituting the values, you'll get cos 30 degree by 2, that is 0.9659 approximately. So this is the pitch factor or the coil span factor for the winding given in the question. Right? Now let us move to the second question here. The question is, a three-phase 20-pole 50 Hz alternator has single layer winding with full pitch coils. So pay attention here that the coils given in this particular question are the full pitch coils, right? The coils are connected in 60-degree phase group and each coil is having 6 turns. Pay attention here as well. Each coil is having 6 number of turns. The flux per pole is 0.25 Weber. Determine the RMS value of EMF induced per phase. The number of slots given in the question are 180, right? So the number of poles for which the winding is wound is 20. The frequency of supply is 50 Hz. The number of slots are 180. Flux per pole is given to us as 0.025 Weber. Number of turns per coil are given as 6. Coil span factor would be equal to 1, or the pitch factor would be equal to 1 because it is given in the question that we are using the full pitch coils, right? The winding is single layer full pitched 3-phase winding. So for determination of EMF equation, for determination of EMF, I mean to say, let us first write down the formula of EMF. Let us just pay attention over the formula of EMF. What all we need? 4.44 kc, kd, phi, f, tph. tph is the number of turns per phase, right? So let us start from determination of tph itself. Number of turns per phase, right? We know that there are total 180 slots. Okay. Each slot is having 6 sides of the conductor, 6 sides, 6 coil sides or the 6 number of conductors, right? So, or I can say that number of turns per coil is 6. So the turns per phase comes out to be 180 multiplied by 6 divided by 3. Number of turns, let us pay attention here. Number of turns per coil are given to us as 6. Each coil is having 6 number of turns, right? So we can very well write here that total number of turns per phase would be number of slots multiplied by number of turns per coil divided by 3 to get the per phase value. It comes out to be 360. So we have got the value of tph. The frequency is given to us as 50 Hz. The flux that we have to use in the equation is also given and its value is 0.25 Weber. What else we need to determine is Kc and Kd. So again, Kc is also given in the question by the mention that the coils are the full phase coils, so Kc becomes equal to 1. So we only need to calculate the distribution factor for this winding. So the distribution factor is given as we know, sin m alpha by 2 upon sin m sin alpha by 2. So I need to calculate m, I need to calculate alpha. So the slot angle alpha is given as 180 electrical degrees divided by number of slots per pole. Number of slots per pole are given as 180. Number of poles are 20. So 180 degree electrical divided by 180 by 20. Solving this, we'll get a slot angle of 20 degree electrical, right? After that, what is left is number of slots per pole per phase. So number of slots, this is number of poles, this is number of phases. So number of slots per pole per phase, that is m, comes out to be equal to 3. Substituting these values in the equation of distribution factor, you will get the distribution factor as 0.9598, right? Now substituting all these values in the EMF equation of the alternator, we will receive the answer as 1917.7 volt. And remember, this is the per phase value of the induced EMF. If suppose it is given to you that machine is star connected or delta connected, and suppose you are being asked that determine the line value of the voltage, then according to the connection of the armature, you will just convert the phase EMF into the corresponding line value. So if the alternator armature winding is star connected, you have to write the line voltage as EL, line value of the induced voltage, or the induced voltage between two terminals of the winding would be equal to √3 times E phase. In case of star connection, if suppose the alternator armature winding is connected in delta, then you will write EL as equal to E phase itself, right? So let us proceed to the third question. Now, the question is, calculate the no-load terminal voltage. Remember, pay attention that they are asking for no-load terminal voltage of the 3-phase 8-pole star-connected alternator, which is running or rotating at a speed of 750 RPM. The other data of the machine is given as follows. Sinusoidally distributed flux per pole is 55 milliweber. Always pay attention towards the unit of the quantity given in the question and never forget to apply the required conversion while solving the equation. Total number of armature slots are given as 72. Number of conductors per slot are given as 10. Then the distribution factor is given as 0.96 and we are assuming the full pitch winding, right? So we need not to bother in this particular question, we need not to bother about calculating the distribution factor, because distribution factor is directly given to you in the question as 0.96 and we have to assume the full pitch winding. Full pitch winding means the coil span factor or the pitch factor is going to be equal to 1. Right? So let us now solve the question. So first of all, just keep in mind what you need to determine. You need to determine the induced EMF, no load terminal voltage. No load voltage available at the terminal is nothing but the induced voltage in the machine. Right? So first of all, let us pay attention towards the equation of the induced EMF 4.44. Kc F by dph. Right? Kc is known to us. Kd is known to us. phi is given in the question. So for solving this equation, we need to determine the frequency which is not given in the question this time, and TPH, number of series connected turns per phase, right? So for determination of frequency, just pay attention over the data that is given in the question. We know the number of poles, we know the operating speed of the machine. So using Ns equals to 120 F by P and converting and rewriting the equation for determination of frequency, that comes out to be Pns upon 120. We can very well solve. Number of poles are given as 8. The speed at which machine is rotating is 750 and 120 is a number which is constant. Solving this, we will get 50 Hertz as the supply frequency, right? Besides this, so we have got the frequency as well, right? What else we need to calculate is TPH. What is TPH? TPH is the number of series connected turns per phase. So, for determination of TPH, the data is given to you in the question. Number of slots are given to you. Number of conductors per slot are given to you, right? So, number of turns per phase becomes 72 multiplied by 10 by 2 divided by 3, right? 72 multiplied by 10 conductors per slot, right? So, the numerator is giving to you the total number of conductors distributed in 72 slots throughout the armature periphery, and denominator is giving you a division by 2 is giving you total number of turns throughout the periphery of the armature, and division by 3 is giving you the number of series connected turns per phase, right? It comes out to be 120. So solving this, you will get an induced EMF per phase value as 1406.6 volt, and as the alternator is connected in star, the no load value of the terminal voltage would be √3 times of what we have calculated here. So it comes out to be 2436.3 volt approximately, right? Now let us proceed to the next question. The question is based upon the determination of the induced EMF when the alternator is operating at certain power factors. At unity power factor, at 0.75 lagging power factor, and at 0.75 leading power factor. So let us try to understand what question is asking. A single phase 100 kVA 600 volt 50 Hz alternator has effective armature resistance and leakage reactance of 0.072 and 0.18 ohm respectively, right? At rated terminal voltage and kVA load, determine the internal induced EMF at unity power factor, at 0.75 lagging power factor, and at 0.75 leading power factor. Okay. So, the rating of the alternator is given to us. Besides this, effective armature resistance and leakage reactance is also given to us. The terminal voltage of machine is known to us. The kVA rating of the machine is known to us. Then we are asked that at rated terminal voltage and kVA load, we need to determine the induced EMF, right? So for determination of induced EMF, knowing the terminal condition, the equation is defined for unity lagging and leading power factor. For considering the first case of unity power factor loading, the equation is under root V cos phi plus IARA square plus IAXL square, right? What is V over here? V is rated voltage per phase, right? What is I over here? If we need to determine the induced EMF under rated load and rated voltage condition, I is going to be the rated current, right? R is given to us, XL is given to us. They are respectively the effective armature resistance and the leakage reactance. Besides this, cos phi is the operating power factor of the machine. Cos phi is the operating power factor, and in this particular case, the machine is operating at unity power factor, right? So just substituting the values. Before that, I need to determine the rated current. So rated current is given as rated kVA divided by the voltage. It is a single phase alternator, right? So simply rated kVA divided by rated voltage will give us the rated current. Substituting the values, you will find that the induced EMF is 612.73 volt. Just keep this value in mind while we are discussing the second and third part of the question. In second part of the question, the induced EMF is given as under root V cos phi plus IR square plus V sin phi minus IXL square. Just substitute all the values. Cos phi is given to us as 0.75. Sin phi can very well be calculated and it comes out to be 0.6614. Substituting the values and solving this, you will find that this is plus. You will find that the induced EMF comes out to be 629 volt. Keep this value again in mind. Compare it with the previous one. 612 was the value obtained here. 629 is the value obtained over here. Now let us proceed for the leading power factor case. This is the equation. Just substitute all the values. The power factor is same, 0.75. So value of the power factor will remain same, cos phi and the sin phi. Solving this, you will obtain a voltage of 590 volt. Just compare all these three voltages. Right, what you can see? You can very well see that terminal voltage is more in case of the leading power factor operation of the machine. The terminal voltage would be less than the induced voltage in case when machine is operating at unity power factor as well as its lagging power factor. But when the machine is operating at leading power factor, the terminal voltage is more than the induced EMF. Right? And this happens because of presence of capacitance in the load circuit. So that's all for today's lecture. Thank you.